Hello everyone, I'm Dakota Murray, filling in for our entire team to talk to you today about the emergence of hierarchy in faculty hiring networks. Now, as many of you may know from your own experiences, faculty hiring is incredibly competitive and driven by prestige. For example, the vast majority of movement in hiring is movement down the hierarchy. And this hierarchy is steep. Only 7% of employed faculty have a PhD from the lower 75th percentile of universities. There are also many known biases, such as those that affect women when they enter the job market. However, not a whole lot is known about the mechanics of how these hierarchies actually emerge in hiring networks. And so, in response to this gap, we introduce a simple model, a network model of hierarchy that goes something like this. Given two departments, A and B, when Department A hires a candidate who graduated from Department B, then we consider Department A to have endorsed Department B. More typical of a hiring cycle, there are many such hires between departments, each conferring endorsement from one to another. From this network of endorsements, we can construct a set of prestige rankings. If this model looks familiar to you, that might be because it was presented earlier at this conference by Mari Kawakatsu, who presented a more sophisticated variant of this model, focusing on its mathematical characteristics. Here, however, we're taking a different approach. In contrast to the more sophisticated model used in Mari's talk, we're going to focus instead on a more simplified model that's more amenable to simulation. And using simulation, we want to try to get a better qualitative understanding of the characteristics of the model and see if we might extract insights from the simulations to help inform our own understanding of faculty hiring. The key idea of this model is that prestige is calculated from an endorsement network using Spring Rank. In a round of hiring, each department makes offers to graduates based on the prestige of their alma mater. The decision is also based on another parameter, beta, which dictates the department's sensitivity to prestige. In the same way, graduates also choose among their offers based on the prestige of the department, with graduates preferring more prestigious jobs. Once a graduate chooses an offer, then an endorsement link is established between the two. Note that this model allows for department openings to go unfilled, as well as for candidates to leave without an offer. We repeat this process over many iterations, each time using the set of previous endorsements to inform the new decisions. To enforce a finite memory on the model, we also introduce a memory parameter, t, such that endorsements older than t iterations are removed. The simulation goes something like this. We make a selection for each of the model parameters, here setting the number of candidates and openings per department uniform across all departments. And then we initialize a random endorsement network, which is then used to compute a set of prestige rankings. Using these rankings, we inform decisions to create a new endorsement network, from which we create another set of rankings. And we repeat this process over 100 iterations. After running the simulation, we can start to look at how the model actually behaves. Here, we're going to limit to 150 departments and have 10 candidates per department. However, all other variables can be varied. Here, we calculate the rolling Gini, or inequality index, of the gammas of each department. Here, we calculate a measure based on the gamma across all departments. Gamma is a value from the internals of the model that roughly corresponds to the likelihood that a department is selected during a hiring decision, or in other words, its prestige. The Gini index is an index of the inequality across the gammas. The key idea is that a higher Gini index corresponds to a more unequal system of hiring. We also vary the parameter beta, the sensitivity to prestige, shown here with the letter B. And as we would expect, higher sensitivity to prestige leads to a more unequal hiring system. The dotted line shown in this plot is the level of inequality in the real-world faculty hiring network found in previous research. Now, varying the value of memory, t, we can see that longer memory produces a more stable hierarchy. This is a pattern that's similar across different configurations of the system, both in high and low competitive ones. More memory leads to more stability. We also find that more competitive systems are more unequal, such as those in the top row where we have 10 candidates competing for one position per department. The parameters here that best capture the level of real-world inequality in faculty hiring involves the case of a competitive system with long memory and high sensitivity to prestige. We can also look more deeply at the interaction between prestige sensitivity beta and the memory parameter t. Here we show the average Gini coefficient across all 100 iterations of the model for different values of these parameters. We find that the largest inequality is produced in low memory, high prestige systems. Looking at the impact of competitiveness at this extreme, we see that it is highest when there is only one position available per one department. Similarly, we can also look at the stability of the system, here measured using the standard deviation of the Gini index across all iterations of the model. We find that the hierarchy is less stable when it is more prestige sensitive and has less memory. And also, at this extreme, the rankings are the least stable in non-competitive systems. A benefit of the simulation is that we can look at some interesting scenarios that would be much more difficult to approach using mathematical analysis. For example, what happens when a new department enters the hierarchy? To simulate this, we run 100 iterations of the model, and after the 100th iteration, expand with a new department with a preset rank. Then we can see what happens with this new department in the subsequent 100 iterations. So, adding a new low-ranked department, we find that it ends up still being a low-ranked department at the end. Adding a mid-ranked department, we see that it does fall in rank, but still ends up higher than the low-ranked one. However, adding an elite high-ranked department, we see that it ends up, in the end, still being one of the most top-ranked departments in the simulation. The conclusion here is that under this model, where you start really matters. Initial ranks are reinforced by the dynamics of the model. So, to summarize, by exploring this model, we find that unequal hierarchy emerges from high sensitivity to prestige and short memory. However, stable hierarchies emerge from long memory. Especially competitive hiring systems are more unequal overall, as well as being less stable. And when a new department enters, initial conditions reinforce future prestige. Now, while these findings are all based on a simple model, they can still help us inform our reasoning about real-world mobility. For example, we can look at the regimes produced by the model and think about what regimes might mimic real-world hiring and what sort of parameters might produce them. If our goal is to reduce inequality in faculty hiring, then this model tells us that reducing the sensitivity to prestige might be the most direct and effective strategy. But we also need to think about our values. How do we as a community want faculty hiring to look? For example, is inequality okay if the hierarchy is unstable and tends to change over time? Different community values will require different policy interventions, and this model gives us one way of exploring those interventions and those strategies. Hiring is the result of a series of choices by departments and graduates, and this model shows how prestige preferences drive these individual choices and how, collectively, they can inform the larger hiring network. Moving forward, we hope to build on these preliminary results. The most clear next step for our research is fitting the model to real-world faculty hiring data. In the work presented earlier in this conference, they fit a version of this model to the hiring patterns of math PhDs using the Mathematics Genealogy Project, and identified evidence of positive, non-zero sensitivity to prestige. We hope to extend their work with larger and more diverse data, such as that taken from bibliometric databases. Once fit to real-world data, we hope to use this model to address policy-relevant questions. For example, how can strategic hiring decisions affect a department's rank? And how can policies at different levels of governance impact the dynamics of faculty hiring more generally? We also aim to address the extent to which other covariates impact hiring, such as gender and nationality. So, stay tuned for more of the work. In the meantime, I want to thank my team so much for making this work possible. If you have any questions or comments, please feel free to reach out to myself or Mari using the information listed here. In the meantime, I hope that you enjoy the rest of the conference.